As promised, the tabular method for integration by parts. Instead of doing integration by parts 4 times, this is kind of like synthetic division to long division. It's just another way of doing the same process. Some people like the tabular method for all of the problems we just did. I don't, but some people do, and that's fine. It's just another way of doing the same stuff. It's just kind of a shortcut sometimes. So what we're going to do is we're going to create a column for derivatives and another column for integrals. And as we saw in the last problem, right, where it was x to the second instead of x to the fourth, the polynomial x squared was what we were differentiating because it got simpler as we differentiated. So the same thing here. We're going to take that x to the fourth and put that in the derivative column. So everything else has to go in the integral column. So that's going to be the sine of x over 3. So when you're using the tabular method, what you really want to see is something in the derivative column that will differentiate down to 0. Polynomials will always do that. And then putting something in the integral column that you can integrate over and over and over again. Trig functions, well, sine and cosine at least, fit that description pretty well. So does e to the x. So we'll do that. We'll take the derivative of the left side column until we get down to 0. So 4x to the third, 12x squared, 24x, 24, and finally 0. So as many rows as we have over here, we have to have that many rows over here. So remember, we're integrating, not differentiating. So we're not going to have a 1/3 here. That's the biggest mistake people make here. But we're going to have a 3 here. We're dividing by 1/3. Sine goes to negative cosine if you're integrating, right? That's the other mistake. People will just go to positive cosine because they're thinking derivatives, but no, we're integrating. So we're going to keep on multiplying by 3 on each of these steps. So this is going to be negative 9 sine of x over 3. And then we're going to multiply by another 3, so this is going to be a positive 27 because the sign is going to flip the sign. And we're going to keep on multiplying by 3, so that's going to be an 81. Integral of cosine goes to sine. And then finally, one more 3 will take us to 243. And we're just integrating over and over and over again. Now, remember that the integration by parts formula, let's find it just written here, has a minus sign in it, right? This minus is part of the problem. So part of the formula here. So that means basically we're going to flip the signs each time. So that's where this next step comes into play. We're going to do a plus for the first one and a minus for the second and a plus and a minus. And we just alternate pluses and minuses down. And that's the minus in the formula. And then we multiply across, but we multiply diagonally across. So we go x to the fourth times this one down here. And we go negative 4x cubed times this one down here. Positive times this one down here, negative times this one down here, positive, and we don't end up using the 0. The 0 is just there to tell us to take this column all the way down here. We also don't end up using that first integral. These are not part of the final answer. So everything else is part of the final answer. So our final answer is going to be this term times this term, so that's going to be negative 3 x to the fourth times the cosine of x over 3. That's our first term. Our second term is going to be negative 4x cubed times negative 9 sine of x over 3. So that's negative 4 times negative 9 is a plus 36. And the hardest part about this whole process is just actually writing out the answer because the answer is so huge. The next one is going to be positive 12 times positive 27. And I could do that by hand, but I don't want to, so I'm going to go ahead and use a calculator to get 324 x to the second times cosine of x over 3. The next one is going to be negative 24 times positive 81, so negative times positive, so negative. And then my calculator tells me that's going to be 1944, the year of my father's birth. And that's going to be, we're back to sine, right? The trig functions are going to alternate. And then one more, right? We've got the 24 times negative 243, so minus 24 times 243 works out to be 5,832 times the cosine of x over 3. And that's the tabular method. That's a crazy final answer. This is not something that I would want to check by hand unless I really had to. This is something that I might punch into a calculator to double check. But that's a nice time-saving technique rather than doing the longhand integration by parts. Great. So that's the tabular method. Use that when one of your pieces differentiates down to 0. So we could use this on the next one. I'm not going to, because I only like the tabular method when it goes several iterations. If it's 2 iterations or more, then I'd probably use the tabular method. Anyway, so this next problem, example 5, should look kind of familiar because we've done this in the past. We've done this using U-substitution, and if you recall, we let the thing inside the parentheses be our U value, and then you're saying, but wait a second, what about that X on the outside? Well, we had to do a little bit of extra substitution. If U equals X plus 1, then that means that U minus 1 equals X, so we're going to replace this X with a U minus 1, we're going to replace this X plus 1 with a U, and the dx equals du, so everything works out pretty nicely. That's the old way of doing it. Turns out we can also attack this problem using integration by parts, so we're going to do that this way instead. So as you might expect, we're going to let the derivative side of things be x, because that differentiates nicely, and then dv is going to be the other piece, the square root of x plus 1. I'll write it in exponent form because that makes things a little nicer. So anyway, when we take the derivative on this equation, we get du equals dx. When we take the integral on this one, we don't have to worry about the chain rule because the derivative of x plus 1 is 1. So we've got this x plus 1 to the 1/2 plus 1 is 3/2, and then we've got a 2/3 out front. All right, so we got something simpler over here. Maybe it's a little bit more complicated over here, but hopefully the simpler coefficient of 1 here will make things simple enough. So let's see how this works. U times v is x times 2/3 x plus 1 to the 3/2 minus the integral of v du, so 2/3 x plus 1 to the 3/2 du is dx. This integral is easier than the original one, even though it's got a higher exponent because it doesn't have that extra x out here. So we can go ahead and actually do that problem, right? So this is 2/3 x times x plus 1 raised to the 3/2 minus 2/3, and then the integral of this. So the x plus 1 to the 3/2 plus 1 is 5/2, and then divide by 5/2, multiply by 2/5, and that's your final answer. We probably won't leave this one like this because it does factor so nicely. One thing you'll notice is that there's a 2/3 in both of them. And there's also an x plus 1 to the 3/2 in both of them. So if we factor that out, then we're left with just x in the first term, minus 2/5. And the x plus 1 to the 5/2, we took 3/2 away from there, so we're going to have one factor left. And yeah, I suppose we could leave it like that, but let's factor out, since we've got a fraction here, let's factor out that 1/5. 2/3 times 1/5 is 2/15. So we're going to divide everything inside this parentheses by 1/5. In other words, multiply by 5. So this is going to be 5x minus 2 times x plus 1. Now I'll just take it one step further and distribute and combine like terms. So 5x minus 2x is 3x, and negative 2 times 1 is negative 2. And that is your final answer. This is what I would put as the answer choice in a multiple choice question like this. I wouldn't want you to stop in any of those other earlier ones. Now, just for fun, I, in advance, worked this out the old method of U-substitution, and you can see over here that we ended up in the same place. So if you needed a quick refresher of how that looks, I didn't show every single step because I was just doing a quick check to make sure I ended up in the same place, and lo and behold, I got the exact same answer. So that's a nice nice comparison of the methods. It's not that one is better than the other, it's just two different ways of doing the same thing. All right, this next problem looks a little odd because it looks like there's only one part. So sometimes we'll see that. Sometimes we'll see that this is an integration by parts problem, and there's not much to do. Remember that the dx has to be here, right? And if we put the ln x over here as well, then we're just back to where we started. So that's not going to get us anywhere. So just put the dx alone over there, and then the ln x goes over here. Remember earlier when I said we couldn't pick dv equal to ln x dx? Well, this is actually going to be something that we might want to consider memorizing. The integral of the natural log of x might come in handy. You don't have to memorize it. You can go through this process each time. It's not so bad. Du is 1 over x dx. V equals x. So when we apply our integration by parts formula, we get u times v, so natural log of x times x minus the integral of v du, x times 1 over x dx. And this doesn't simplify, it's just natural log of x times x, or flip it around. And then this is x times 1 over x is just 1. So the integral of 1 dx is just x, so minus x plus c. And that's a pretty common way to write the final answer. You'll also see people write it like this, with the factored form. I like them both, so I'll box them both in. I don't think one is any better than the other. They're both useful, so know them both. Now, number 7 is going to look pretty similar to that one, in that it doesn't seem like it has enough parts. So let's try this the same way. We're going to let u equal the integrand, the whole integrand, because it's only one term, and then dv is going to equal dx. So that dv equals dx is going to turn us into v equals x again. This time you have to remember your arctan derivative, and that's 1 over x squared plus 1 dx. And the nice thing about this is it gets rid of the inverse trig function, just like it got rid of the natural log function here. So these are derivatives that may be a little messy, but they're better than the original. So when we do u times v, we get arctan of x times v, which is x, minus the integral of v, oops, v is x, times du, which is 1 over x squared dx, x squared plus 1 dx. That plus 1 is significant. So unlike here, where the x is just canceled out, we have this plus 1 here, so it's a little bit more involved. So let's see, we've got x times the arctan of x minus the integral of x over x squared plus 1 dx. Now we have to try to deal with this rational function. And you might recall that we've done problems like this before. That integral requires U-substitution, so we'll let u no longer equals the arctan of x. We're done with that. Now we're going to let u equal the denominator. That means that du over dx equals 2x, or du over 2x equals dx. So when we rewrite this, we're going to get x times the arctan of x. That part is part of our answer. Minus the integral of x over u times, we'll replace the dx with du over 2x. And as we hoped, those go away. So we end up with x times the arctan of x minus the integral of 1 over 2u, or 1/2 the natural log of the absolute value of u. So our final answer is x times the arctan of x minus 1/2 the natural log of the absolute value of whatever u is, which is x squared plus 1. That's kind of a fun answer. You wouldn't really expect natural logs to be in the answer when you take the antiderivative of the arctan, but lo and behold, that's how it works out.